This video is an overview of atomic orbital shapes based on quantum numbers. If you want an overview of quantum numbers, go check out the other video that I posted today. We're going to start with L equals 0, which we said denotes an s orbital. S orbitals are spherical in shape. This applies no matter what the n value is that the s orbital falls under. If we have n value of 1 and an L value of 0, that's a 1s orbital. Its electron distribution spikes fairly close to the nucleus and then tapers off very quickly. If, however, we go up to n equals 2, so the second orbital shell, you can still have an n equals 2, L equals 0 suborbital, so a 2s suborbital or subshell. That 2s orbital has a node in its electron distribution function. That node is a place where you're not likely to find an electron at all. If you look at the scatter plot, that shows up as a band of no electron density. Moving up to the 3s, so n equals 3, L equals 0, you can see we've got two nodes in the distribution function and therefore two bands of no electron density. Now these still are spherical shaped, it's just that inside the higher energy level s orbitals have these bands of no electron density and higher electron density. The other important thing to note is that as you go up in n energy level, 1 to 2 to 3, the orbitals themselves get larger and the electrons move farther away from the nucleus. Also note, L equals 0, therefore m equals 0, so the s orbital has only one subshell. These nodes do not denote new subshells. They're still part of that same 2s or 3s subshell. What about higher L number orbitals? If L equals 1, we said that was a p orbital. If L equals 1, then m can equal -1, 0, or 1. Therefore, a p orbital has 3 subshells. So you can see 1, 2, 3. This is the composite view. At n equals 2 or higher, you can have p orbitals. And they always have the same overall shape, although at higher energy levels, like n equals 3 or n equals 4, these orbitals can have nodes within them just like the s orbitals can. Let's keep going. If L equals 2, that's a d orbital, and m can be -2 to +2. Therefore, a d orbital has 5 subshells, 1, 2, 3, 4, 5. And these, just like the p orbitals and the s orbitals, can have nodes within them if you're at a high n value. And these types of orbitals show up at n equals 3 or greater. Lastly, at L equals 3, we have f orbitals, which look like this. If L equals 3, then m can be -3 to +3, and the orbital has 7 subshells. 1, 2, 3, 4, 5, 6, 7. This is the most complex orbital shape that you are likely to encounter in the current periodic table. And again, just like all the other orbitals, at high n values, you can have nodes within these suborbitals, bands of higher and lower electron density. Starting next week, we're going to find out how these orbitals come together to start describing not just atomic shape and properties, but also some of their chemistry. So see you on Monday.